Somewhere out there, an object could be sitting in plain sight, pretending to be something it isn't. It has the mass of a collapsed star. It bends light into the same dark silhouette we photograph and call a black hole. Distant stars swing around it in the very same orbits, and yet, at its heart, there is no crushing singularity, no point of infinite density, no one-way door in space-time from which nothing returns. Instead, something stranger holds it up from the inside, a pocket of exotic emptiness pushing outward against the weight of collapse. If such a thing exists, we may already be looking straight at one, mistaking it for the very object it imitates. So how would we ever tell the difference? The clue may lie in its surface. Before we go further, if you enjoy following ideas like this all the way to the edge of what we actually know, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Picture the most extreme object you can imagine. Several times the mass of our sun, sometimes far more, crushed down into a ball only a few dozen kilometers across. The gravity around it is so ferocious that the fabric of space and time is bent almost to breaking. Reach a certain distance from the center, and the pull becomes so strong that not even light can climb back out. That final boundary, that point of no return, is what we call the event horizon. And everything we have been taught says that once matter falls inside, it keeps falling until it is crushed into a single point of infinite density our equations can no longer describe. We call that point the singularity. Together, the horizon and the singularity are the two defining features of a black hole. They are the reason black holes feel less like objects and more like holes torn in reality itself. Now, here is the strange idea we are going to sit with. What if you could build something that had almost all of that from the outside? The enormous mass, the tiny size, the crushing external gravity, the ability to bend starlight into a dark silhouette, but none of it on the inside. No horizon, no singularity, no one-way door. Instead of a bottomless pit, imagine that the collapse stops. Something pushes back. Something fills the interior with a kind of exotic emptiness that refuses to be crushed any further. From a great distance, you would swear you were looking at a black hole. Up close, it would be a completely different kind of beast. This hypothetical object has a name. It is called a Gravastar. Let me be very clear about something right at the start because it matters more than almost anything else we will say. A Gravastar has never been seen. It has never been detected. It has never been confirmed to exist anywhere in the universe. It is not a discovery. It is a proposal, a theoretical possibility worked out on paper using the mathematics of general relativity. When physicists talk about Gravastars, they are not describing an object they found in a telescope. They are describing something that the equations seem to permit, and then asking a careful question. If such a thing could exist, how would it behave? And could we ever tell it apart from the black holes we think we already see? So everything that follows is a description of a hypothesis. Hold that thought in the back of your mind the entire way through. We're exploring what might be, not what has been proven to be. The name itself is a clue, and it is worth taking apart slowly. Gravastar is a compression of a longer phrase, gravitational vacuum star. 3 words, and each one is doing real work. Gravitational because the object is held together and shaped by gravity, just like any star or collapsed remnant. Vacuum because the heart of the object is proposed to be not ordinary matter at all, but a peculiar vacuum-like state, a region where the emptiness of space itself has been given strange physical properties. And star, because from the outside it sits in the same family as the other dense, compact things that stars can leave behind when they die. Gravitational vacuum star, an object whose gravity wraps around a core of exotic vacuum instead of a core of crushed matter or a naked singularity. Once you hear the name unpacked, the whole concept starts to make a little more sense. The vacuum is the point. The vacuum is what replaces the thing we fear. The idea was put forward at the very start of this century by two physicists, Pavel Mazur and Emil Motola. They were wrestling with the discomfort that many people who study black holes quietly share. The classical black hole, for all its elegance, contains features that make physicists uneasy. The singularity at the center is a place where density becomes infinite, and the known laws of physics simply stop giving sensible answers. The event horizon raises deep puzzles about what happens to information that falls inside. So Mazur and Motola ask whether general relativity might allow a different ending to gravitational collapse. Instead of matter plunging all the way down to a singularity behind a horizon, what if the collapse could halt just before the horizon formed, and the interior could settle into a stable, exotic configuration? Their answer was the Gravastar. I want to introduce them and then move on quickly, because the point of our journey is not the history of who wrote which paper. The point is the object itself, the physics of it, and the tantalizing possibility that it could be masquerading as something else. So let us build the thing in our minds, piece by piece. In its original and simplest form, the Gravastar is described as having three regions nested inside one another, like the layers of an onion. Understanding these three regions is the key that unlocks everything. The first region is the interior, the very heart of the object. This is the exotic part, the vacuum-like core, and it is where the concept becomes genuinely alien. In an ordinary star, the interior is packed with hot, dense matter. Plasma, atoms stripped of their electrons, all of it pressing outward because it is hot and being squeezed. In a neutron star, the interior is an almost unimaginably dense sea of neutrons jammed together. But in a Gravastar, the proposal is that the interior is not made of ordinary matter in the usual sense at all. It is a special state of the vacuum, a region where space itself carries energy and, crucially, carries an unusual kind of pressure. And this is where I have to slow right down, because we are about to meet the single most misunderstood idea in this entire subject. The interior of a Gravastar is proposed to have negative pressure. Now, the moment people hear the word negative, alarm bells go off and they leap to a conclusion that is completely wrong. So let me draw a firm line here. Negative pressure does not mean negative mass. It does not mean the matter weighs less than nothing, or falls upward, or is somehow anti-gravity in the science fiction sense. Those are different concepts entirely, and confusing them will lead you astray. Negative pressure is a real and respectable idea in physics, and you already live inside a universe that contains it. Let me give you a way to feel what pressure even is. Ordinary positive pressure is a push. The air in a balloon presses outward on the rubber. The gas in a hot star presses outward against the crush of its own gravity. If you could grab a chunk of that gas and try to squeeze it, it would push back at your hand, resisting. That resistance, that outward shove, is positive pressure. Now think about the opposite. Think about tension, like the tension in a stretched rubber band or a pulled spring. A stretched rubber band does not push outward, it pulls inward. If you let go of one end, it snaps back toward the middle. That inward pull, that tension, is in a real sense negative pressure. It is the tendency to contract rather than expand. Ordinary substances can have this. A solid under tension, a stretched membrane, a rope pulled taut, all of these carry a kind of negative pressure along the direction they are stretched. But here is the twist that makes the Gravastar so counterintuitive, and it comes straight out of Einstein's theory of gravity. In general relativity, pressure is not just a mechanical force. Pressure itself has weight. Pressure itself gravitates. Positive pressure, the outward push, actually adds to gravity. It helps pull things together, which is one of the reasons very massive stars are doomed to collapse, no matter how hard their insides push back. But negative pressure does the reverse. Negative pressure spread uniformly through a region of space produces a gravitational effect that is repulsive. It pushes space-time apart rather than pulling it together. And this is not exotic speculation dreamed up only for Gravastars. It is the very same kind of effect that physicists invoke on the larger scales of the cosmos to explain why the expansion of the universe is speeding up. A vacuum energy with negative pressure produces a gravitational repulsion. The Gravastar takes that same idea and puts it to work in a tiny, incredibly dense package. I want to give you one more way to feel this, because it runs so hard against ordinary intuition that a single pass is rarely enough. In everyday life, we think of weight as coming from stuff, from how much matter is packed into a thing. More matter, more weight, more gravity, and that is true. But Einstein taught us that gravity does not respond only to matter. It responds to energy and to pressure as well, all of them together. Every form of energy gravitates, and pressure, the push or pull inside a substance, gravitates too, adding its own contribution to the total pull. When the pressure is positive, an outward push, it adds a little extra gravity, a little extra tendency to draw things together on top of the gravity of the matter itself. This is quietly astonishing already. The very outward push that mechanically holds a star up is, gravitationally, also helping to crush it. But flip the sign, and everything reverses. When the pressure is negative, an inward tension, its gravitational contribution flips too, becoming a push apart rather than a pull together. Pile up enough negative pressure in one place, and its repulsive gravitational effect can overwhelm the ordinary inward pull, so that the region as a whole tends to fling space-time outward. That is the strange lever the Gravastar pulls. It is not defeating gravity with some anti-gravity substance. It is using gravity against itself, feeding it a diet of negative pressure so that gravity's own response becomes a push outward instead of a pull in. So now you can see the whole trick of the interior. The heart of a Gravastar is filled with this vacuum-like energy carrying negative pressure. And because negative pressure gravitates in a repulsive way, that interior pushes outward, not with a mechanical shove like hot gas, but with the strange anti-crushing tendency of a repulsive gravitational effect. It resists the collapse. It holds the object open from the inside. Where an ordinary collapse would drive all the matter down toward a singularity, the exotic interior of a Gravastar is proposed to prop everything up, halting the fall just short of the point where an event horizon would otherwise form. The singularity never happens, because the collapse never completes. The horizon never forms, because the surface stabilizes just outside of where it would have appeared. That, in one sentence, is the beating heart of the entire idea. an exotic vacuum with negative pressure resisting the final plunge into a black hole. Let me repeat the warning one more time, because it is that important. This outward resistance is not the interior having negative mass. The energy in there is real, positive energy. It is the pressure that is negative, and it is the peculiar way that negative pressure interacts with gravity in Einstein's theory that produces the outward supporting effect. Negative pressure, positive energy. Keep those two ideas locked in their proper places, and the physics stays honest. Now we come to the second region, and it is just as important as the first. If you have a bizarre, repulsive, vacuum-like interior on the inside, an ordinary, familiar, attractive space-time on the outside, then something has to join them together. You cannot simply have exotic anti-gravity vacuum on one side of a line and normal space on the other with nothing in between. There must be a transition, a boundary, a place where one kind of physics hands off to the other. In the Gravastar model, this boundary is an extremely thin shell, and it is not gentle. This shell is a razor-thin layer of matter, incredibly dense, squeezed into a skin that might be only a tiny fraction of the object's width, in the most idealized versions almost infinitely thin. It is this shell that carries the load. It sits at the crossover point, absorbing the outward push of the exotic interior on one side and the inward pull of gravity on the other, and it holds the whole structure in balance. Think of it as the wall of a pressure vessel, a membrane stretched tight between two opposing tendencies. Without the shell, the object could not exist. The shell is what makes the balance possible. And here I need to add a caution that runs through this entire subject, because it is easy to fall into the trap of thinking there is one single agreed upon blueprint for a Gravastar. There is not. The picture I have just described, a smooth exotic interior, an infinitely thin shell, and ordinary space outside, is the original, idealized version. It is the cleanest, simplest form of the idea, the version you draw first to understand the concept. But in the years since it was proposed, physicists have explored many variations. Some models replace the razor-thin shell with a thicker transition layer, a graded region where the physics changes more gradually from inside to outside. Some models give the interior and the shell different physical descriptions, different equations relating pressure and density, what physicists call different equations of state. Some models consider Gravastars that spin, which complicates everything, and some consider layers upon layers rather than a single clean boundary. So when we speak of the three-region Gravastar, understand that this is a family of ideas, not a single fixed object. The original three-region model is one member of that family, the founding member, but it is not the only way the concept has been drawn. Different assumptions about that shell, about the interior, about the transition, lead to genuinely different objects that all wear the same name. The third region is the easiest to describe, and yet it is the one that makes the whole story dangerous, in the sense of being hard to catch. The third region is simply the outside. It is the exterior, the space-time that stretches away from the object into the rest of the universe. And the remarkable, almost mischievous fact is this. In the idealized case, the exterior of a compact, non-spinning Gravastar can look essentially identical to the exterior of a black hole with exactly the same mass. From out there, in the region where planets might orbit, or gas might swirl, or light might pass by, The geometry of space and time can match a black hole so closely that the two become extraordinarily difficult to tell apart. We are going to spend a great deal of time on why that is true and what it means. For now, simply plant the flag. The interior is radically different, the boundary is exotic, but the exterior can be a near-perfect impersonation. So that is the anatomy. An exotic vacuum-like interior with negative pressure, resisting collapse. A thin, dense shell holding the balance, and an exterior gravitational field that can wear the mask of a black hole. Now let us step back and place this creature in the zoo of dense objects, because the best way to understand what a gravastar is proposed to be is to compare it side by side with the things it is not. Start with an ordinary star. Like our own sun, a star is a furnace. Deep in its core, hydrogen is fused into helium, releasing torrents of energy. That energy flows outward as heat and light and radiation pressure, and this outward push of hot gas and radiation is what holds the star up against the relentless inward pull of its own gravity. It is a balancing act, a war fought every second between fusion pushing out and gravity pulling in. A star is enormous, diffuse by comparison to what comes later, and its support comes from being hot and actively burning. A gravastar is nothing like this. It is not burning. There is no fusion holding it up. It is not diffuse, and its support does not come from heat at all, but from the exotic negative pressure of its interior. A star is a bonfire holding back the dark. A gravastar is something cold and strange holding back a collapse. Now consider a neutron star, which is already one of the most extreme objects known to actually exist. When a massive star dies and its core collapses, if it is not quite heavy enough to become a black hole, it can be crushed into a neutron star. Here, the electrons and protons are forced together into neutrons, and those neutrons are packed so tightly that a single sugar cube-sized piece would weigh as much as a mountain. What holds a neutron star up is a strange quantum effect called degeneracy pressure, the stubborn refusal of neutrons to be squeezed in the same state, plus the forces between the particles themselves. It is a real, physical, matter-based pressure. A neutron star is a ball of the densest ordinary matter the universe can make before gravity wins. A gravastar, again, is different. Its support is not the degeneracy pressure of packed neutrons. Its interior is not a sea of particles at all in the ordinary sense, but that exotic vacuum. A gravastar might be roughly the size a black hole of the same mass would be, even more compact than a neutron star, and yet it avoids becoming a black hole not by piling up more resistant matter, but by switching to an entirely different kind of support. This is the crucial distinction. A neutron star resists with matter. A gravastar resists with vacuum. And finally, the black hole itself. The object a gravastar is designed to mimic and to replace. A black hole, in the traditional description, has that event horizon, the boundary from which no outward signal can ever escape. Cross it, and you cannot send a message back, cannot shine a light back, cannot return. And at the center lies the singularity, the point where our physics breaks down. A black hole is defined by these two things: the horizon and the singularity, the one-way surface, and the crushing point. Here is the whole heart of our story in a single comparison. The gravastar is proposed to have neither. No true event horizon. No central singularity. Where the black hole has a one-way membrane you can only fall through, the gravastar has a real, physical shell and surface sitting just outside where that membrane would be. a surface that in principle things could strike, bounce off, or interact with. Where the black hole has an infinitely dense point, the Gravastar has a region of exotic vacuum. And yet, from far enough away, they can look the same. Sit with how peculiar that is. Two objects, potentially with the same mass, the same overall size, the same external pull, the same power to bend passing starlight. Distant matter would orbit either one in almost exactly the same way. And still, one of them contains a horizon and a singularity, a genuine hole in the universe, while the other contains a surface and a strange vacuum, a solid thing, in a sense, dressed up in a black hole's clothing. If both could exist, then simply seeing the outside, the mass, the size, the gravity, the dark silhouette, would not be enough to tell you which one you were looking at. You would need something more. You would need to find the seam in the disguise. I want to close this first stretch of our journey by being scrupulously fair about where the idea stands, because it would be easy to get swept up and forget. The Gravastar is not a rival theory that has defeated the black hole. It is not a confirmed object waiting only for a better telescope. It is a serious, carefully constructed hypothesis, one of a handful of proposed alternatives to the classical black hole, and it lives, for now, almost entirely in the realm of mathematics and modelling. Physicists can write down configurations that appear to be mathematically possible. They can describe an interior of exotic vacuum, a thin shell, an exterior that mimics a black hole. But writing down an object that could exist on paper is a very different thing from showing that nature actually builds one. And it is a different thing, again, from proving that any particular dark, massive object we have already spotted in the sky is a Gravastar rather than a black hole. None of that has been done. What we have is a possibility, a well-defined and intriguing possibility, and a set of deep questions that flow from it. Those questions are where the real adventure lies, and they are exactly where we are heading. If a Gravastar has no event horizon, but sits with its surface almost exactly where a horizon would be, then how close can it get to being a perfect copy? Why does the outside of such a compact object mimic a black hole so faithfully that even careful observation struggles to separate them? What would that surface actually be like, given that it is nothing like the solid ground of a planet? And most tantalizing of all, if these things can imitate a black hole's gravity, and even, as we will see, a black hole's shadow, then what would give the game away? What subtle detail in the light around it, or the ripples it sends through space-time, could reveal that no true horizon lies at its heart? We have built the object. We know what it is proposed to be, and just as importantly, what it is proposed not to be. We have a core of exotic vacuum pushing outward with negative pressure, not negative mass. We have a thin, dense shell holding the impossible balance. We have an exterior that can wear a black hole's face. And we have a family of models, not a single rigid blueprint, all exploring the same daring idea that gravitational collapse might have another ending. One without a singularity and without a point of no return. Now we need to understand the disguise itself. How an object with a surface and no horizon could fool us so completely from a distance. And why that near-perfect impersonation is the very thing that makes the Gravastar so hard to rule out. We have built the object. Now we have to understand the disguise. And to do that, we need to focus on the two things a Gravastar is proposed to be missing. The two things that define a black hole, and yet, according to the hypothesis, are simply not there. There is no true event horizon. and there is no central singularity. Everything strange and slippery about the Gravastar flows from those two absences. So let us take them one at a time, slowly, and then see how an object can go missing those defining features and still, from a distance, look for all the world like the very thing it lacks. Start with the event horizon, because it is the more important of the two for our story. In a black hole, the event horizon is not a physical surface. There is nothing there to touch. It is a boundary in space-time, a place defined entirely by what can and cannot happen there. Specifically, it is the surface beyond which no signal, no light, no particle, no information of any kind can ever travel outward again. Inside the horizon, the geometry of space and time is so warped that every possible future path leads deeper in. Outward is no longer a direction you can go. It has been closed off. That is what makes a black hole a hole. The horizon is a one-way membrane, and once something crosses it, the rest of the universe can never receive another word from it. It has, in a very literal sense, left our world. Now here is what the Gravastar proposes instead. There is no such one-way membrane. Nothing has been sealed off. Instead, right around the place where a black hole of the same mass would have its horizon, the Gravastar has an actual physical boundary, its shell and surface. And the difference between those two things, a horizon versus a surface, could not be more profound, even though they might sit almost exactly the same location. A horizon is a point of no return, a threshold in the fabric of space-time. A surface is a thing. It is somewhere the outside universe still connects to. In principle, if you sent a signal toward a Gravastar surface, something could happen there, and a response could come back. Light could reflect, matter could strike it, energy could be released. The one-way door has been replaced by a wall, and walls, unlike doors that only open inward, can be knocked on. That single change from a horizon to a surface is the crack in the disguise that everything else in our investigation will eventually try to pry open. But I have to be very careful about the word surface, because it conjures exactly the wrong image, and I do not want to plant a false picture in your mind. When I say a Gravastar has a surface, do not imagine anything like the surface of a planet. Do not imagine solid ground you could stand on, a crust of rock, a floor with a definite top you could land a spacecraft upon. It is nothing like that. The surface of a Gravastar is not a solid boundary in the everyday sense at all. It is the outer edge of that extraordinarily thin, extraordinarily dense transition shell we described. The razor-thin skin, where the exotic interior hands off to the ordinary exterior. It is a boundary in the structure of the object. A place where the physics changes character. Sitting where gravity is so intense that our ordinary intuitions about surfaces and standing have completely broken down. Calling it a surface is a way of saying there is a real, physical there, a location where the outside universe still has contact, rather than a horizon that swallows everything. But it is a surface unlike any you have ever encountered, buried in gravity so fierce that it barely resembles the concept we use the word for. Hold both ideas at once. It is real, and it is nothing like the ground beneath your feet. The second missing feature is the singularity. In the classical black hole, the singularity is that central point where, according to the equations, all the matter that ever fell in is crushed to infinite density, where the curvature of space-time becomes infinite, and where the laws of physics as we know them stop producing sensible answers. It is, frankly, an embarrassment to the theory, a place where the mathematics confesses that it has run out of road. The Gravastar erases it. In its place sits the exotic vacuum interior, that region of negative pressure holding everything open from within. There is no infinite density anywhere. There is no point where physics breaks down. The collapse that would have driven matter to a singularity was halted before it could complete, and what remains is a smooth, if bizarre, interior, where the black hole has a wound in reality at its center. The Gravastar has a strange but finite filling. Now, I want to be honest and careful here, because it would be easy to oversell this. Removing the singularity sounds like a triumph, and in some ways, it is appealing. Many physicists find the singularity troubling and would love a description of collapsed objects that does not contain one. But we must not claim more than we know. Replacing a singularity with an exotic vacuum region does not automatically solve every deep problem that black holes raise. It does not, by itself, hand us a complete theory of quantum gravity. It does not, on its own, resolve the long-standing puzzle about what happens to information that falls into these objects. The Gravastar offers a different picture, one that sidesteps the singularity. But sidestepping a problem is not the same as solving all the problems in the neighborhood. Some difficulties may simply move to a new address. The exotic interior and the strange shell raise their own hard questions. Questions about what that vacuum really is, whether it is stable, whether nature could ever produce it. So let us say it plainly and move on. The Gravastar removes the singularity from the picture, and that is genuinely interesting. But it does not thereby answer everything, and it would be a mistake to pretend otherwise. So, we have an object with no horizon and no singularity, wearing a physical surface where the one and an exotic vacuum where the other used to be. And now we arrive at the central magic trick, the thing that makes this entire subject so gripping. How can an object that is so radically different on the inside look so nearly identical on the outside? Why would a Gravastar, with its shell and its vacuum core, produce a gravitational field in the surrounding space that so closely matches a black hole of the same mass that we might not be able to tell them apart? The answer lies in one of the most elegant and consequential facts in all of gravitational physics, and it is worth understanding deeply because everything about the disguise rests on it. It comes down to this. The gravitational field outside a spherical object depends almost entirely on the total mass of that object and on how that mass is arranged in terms of its overall symmetry, and remarkably little on the fine details of what the object is actually made of. Let me unpack that because it is the key to the whole puzzle. Think first about something familiar, ordinary gravity as Isaac Newton described it. If you are standing outside a perfectly spherical planet, the gravitational pull you feel depends on the planet's total mass and your distance from its center. That is it. It does not matter, for the pull you feel out there, whether the planet is made of iron or rock or is a hollow shell, so long as it is spherically symmetric and totals the same mass. From outside, a solid sphere of a given mass and a hollow shell of the same mass pull on you identically. The outside field cannot tell the difference. The interior arrangement is, in a sense, invisible from beyond the surface. This old result has a direct descendant in Einstein's richer theory of gravity. In general relativity, there is a famous and powerful statement, often associated with the physicist Birkhoff, that captures the same spirit but for the full theory of curved spacetime. It says, roughly, that the spacetime geometry outside any spherically symmetric object, one that is not spinning, is completely determined by a single number, the total mass. The exterior is described by exactly one solution, the same solution whether the source is an ordinary star, a neutron star, a black hole, or yes, a gravastar. As long as the object is spherical and non-rotating, and as long as you are standing outside all of its mass, the geometry of space and time around you is fixed by the mass alone. The internal structure, whatever exotic or ordinary thing is going on down inside, does not leak out into the exterior geometry. It is sealed away, not behind a horizon, but behind the simple mathematics of spherical symmetry. Now you can see the trick in full. Take a black hole of some mass. Take a gravastar of exactly the same mass, made compact enough that it is nearly the same size, spherical, not spinning. Stand outside both of them. According to this result, the geometry of space-time around each one is described by the same solution, determined by the same mass. The curvature of space, the bending of time, the paths that orbiting objects must follow, all of it matches. From out there, the exterior gravitational field of the compact, non-rotating gravastar closely resembles the exterior field of the black hole, because the exterior does not care what is inside. It only cares about the total mass and the symmetry. And both objects have the same mass and the same symmetry. The disguise is not a coincidence or a clever engineering feat. It is a direct consequence of how gravity works. The outside of a spherical object is a mask that hides the inside almost perfectly. This is why the impersonation is so complete and so troubling. Consider what it means for anything orbiting these objects. Suppose there is a distant star swinging around a black hole in a wide orbit, or a stream of gas spiraling in from far away, or another star locked in a binary dance with a dark object. The orbit that star follows, the shape of its path, the speed at which it moves, the way it whips around at closest approach, all of that is dictated by the exterior gravitational field. And since the exterior field of the gravastar matches that of the black hole, the star would orbit the gravastar in almost exactly the same way it would orbit the black hole. Watch a companion star circle a compact dark object, measure its orbit with exquisite care, calculate the mass of the thing it is circling, and you would get the same answer whether the central object were a black hole or a gravastar. The orbit cannot tell them apart because the orbit only responds to the exterior field, and the exterior field is the same. Think about how much of what we know about dark, massive objects in the universe comes precisely from watching things orbit them. We infer the presence of a supermassive dark object at the center of our galaxy by watching stars whip around a seemingly empty point at tremendous speeds and working out how much mass must be lurking there to bend their paths so violently. We weigh dark objects in binary systems by tracking the motion of their visible companions. All of these methods are exquisite at measuring mass, and mass is exactly the one thing the Gravastar copies perfectly. The very techniques that reveal these objects to us are, by their nature, blind to the difference between a black hole and a horizonless imposter of the same mass. They measure the mask, and the mask is identical. I have to keep stressing a qualification that runs through all of this, because the disguise is at its most perfect only under special conditions. Notice how many times I have said spherical and non-rotating and compact. Those words are load-bearing. The cleanest, most perfect impersonation happens for a Gravastar that is highly compact, squeezed down close to the size a black hole of its mass would be, and that is spherically symmetric and not spinning. For such an idealized object, The exterior match is essentially exact, but real objects in the universe tend to spin, often very rapidly, and spinning changes the story, complicating the exterior field, and, as we will see much later, potentially opening up differences. And the different Gravastar models we spoke of earlier, with their thicker shells or different interior descriptions, need not all produce exactly the same exterior in every detail once you move away from the perfect idealized case. So the strongest version of the claim is this: a compact, spherical, non-rotating Gravastar can produce an exterior gravitational field that very closely resembles that of a black hole of the same mass. That is already remarkable, and it is already enough to make these objects extraordinarily hard to distinguish by their gravity alone. But it is a statement about an idealized case, and the messier reality of spin and varied models is where cracks might eventually appear. Let me pause and draw out just how deep this problem goes, because I do not want it to slip past as a mere technicality. We are used to thinking that if two things are made of utterly different stuff, we should be able to tell them apart. A brick and a balloon of the same size are obviously different because we can see and touch what they are made of. But a black hole and a Gravastar are not like that. Their difference is hidden in a region we cannot directly reach, sealed behind the plain mathematics of the exterior field. The one thing that most powerfully broadcasts an object's presence across space, its gravity, is precisely the thing that is identical between them. It is as if two people had completely different interiors, different thoughts, different histories, and yet cast exactly the same shadow and left exactly the same footprints. So that from the footprints and the shadow alone, you could never say which was which. The gravitational footprint of a compact Gravastar and a black hole can be the same footprint. And for a long time, footprints were nearly all we had. This is the moment to name something important, so that we understand what kind of investigation we are really on. Because the exterior gravity is such a good disguise, telling a Gravastar from a black hole is not going to be a matter of weighing it or watching a star orbit it. Those measurements are wonderful, but they are looking at the mask. To catch the imposter, if there is one, we are going to have to find some way to probe past the exterior, to detect the presence or absence of the two hidden features, the horizon and the singularity, or rather their replacements, the surface and the exotic interior. We are going to have to find a situation where the difference between a one-way membrane and a physical wall actually shows up in something we can observe. And that means looking not at the steady, gentle orbits of distant stars, which respond only to the exterior field, but at more violent, more intimate encounters, at what happens to light and matter that come right up close to the surface, and at what happens when these objects are shaken, struck, or slammed together. That is where the mask might slip. But before we get to slipping masks, we have to confront the disguise at its most spectacular, its most famous, and its most misunderstood. Because there is one image, one kind of observation, that more than any other has entered the public imagination as a picture of a black hole. You have almost certainly seen it. A ring of glowing light surrounding a dark central region, a fiery donut wrapped around a pit of blackness. Many people look at that image and believe they are looking at a photograph of an event horizon, at the actual edge of a hole in the universe. And this is where the Gravastar becomes truly unsettling, because that dark central region, that shadow, may not be the proof of a horizon that people assume it to be. An object with a surface and no horizon at all might be able to cast a shadow that looks nearly the same. I want to set that up carefully, because it is the centerpiece of everything, and it deserves to be understood properly rather than sloganized. We have established that the exterior gravity of a compact Gravastar can match a black hole. We are about to see that the way that exterior gravity bends light can also match, closely enough to produce a similar dark silhouette. And so the very image that feels like a direct portrait of a black hole's defining feature might, in fact, be reproducible by an object that possesses no such feature. The shadow, it turns out, is not a photograph of a horizon. It is something more subtle, and understanding what it actually is will completely change how you see that famous picture. Here is what we have secured so far before we turn to the light. A Gravastar is proposed to lack the two defining features of a black hole. It has no true event horizon, only a physical surface sitting just outside where a horizon would form, a surface utterly unlike the solid ground of a planet, buried in ferocious gravity, and it has no central singularity, only an exotic vacuum interior, though removing the singularity does not magically solve every riddle that black holes pose. Despite these radical internal differences, the exterior gravitational field of a compact, spherical, non-rotating Gravastar can closely resemble that of a black hole of the same mass, because in gravity, the outside of a symmetric object is determined almost entirely by its total mass and hardly at all by its internal makeup. As a result, distant stars and gas would orbit a Gravastar in nearly the same way they orbit a black hole. And the very techniques we use to find and weigh these dark objects, which rely on watching things orbit, are blind to the difference. The disguise is a consequence of the deep structure of gravity itself, not a trick, and it is at its most perfect in the idealized spherical, non-spinning, ultra-compact case. That is the mask. Now we need to see how far the mask extends into the realm of light, into that glowing ring and that pit of darkness, and to understand at last what a shadow really is, and whether an object with no horizon could cast one just the same. You have almost certainly seen the image by now. A fiery ring of light, glowing orange and gold, wrapped around a perfect circle of darkness at its center. When it was first revealed, it traveled around the world in hours, splashed across newspapers and screens everywhere, hailed as the first picture of a black hole. And that is where a small but crucial misunderstanding took root in millions of minds. Because when most people look at that image, they believe they are seeing the event horizon itself. They think that black circle in the middle is the hole, the actual boundary of no return, photographed directly, a portrait of the abyss. And that belief, understandable as it is not quite right. What that dark region actually is turns out to be far more subtle, far more interesting, and far more relevant to our Gravastar than a simple photograph of a horizon could ever be. Because once you understand what a shadow really is, you will understand how something with no horizon at all might cast one that looks nearly the same. So let us take that image apart and rebuild it from the ground up, because this is the heart of the whole matter. First, the most important correction: the dark central region is not a direct photograph of the event horizon. It is not even, strictly speaking, a picture of the horizon's edge. The horizon is far too small and far too specific to be what we're seeing. The dark patch, which astronomers call the shadow, is considerably larger than the horizon itself, and it is produced not by directly imaging the boundary of the black hole, but by the way the object's ferocious gravity bends and captures the light around it. The shadow is a silhouette carved out of the surrounding glow by the bending of light. To understand it, we have to understand how gravity treats light near an extremely compact, massive object, and that is a beautiful story in its own right. Begin with the fact that Einstein gave us over a century ago, and that has been confirmed countless times since. Gravity bends light. Light travels in straight lines through empty, flat space, but space near a massive object is not flat. It is curved, warped by the object's mass, and light, faithfully following the shortest available path, curves along with it. Near the sun, this bending is slight but measurable, enough to shift the apparent positions of stars whose light grazes the sun's edge. But near an object as compact and massive as a black hole or a Gravastar, the bending becomes extreme, almost unrecognizable, compared to the gentle deflection near an ordinary star. Light near these objects does not merely bend a little, it can be swung through enormous angles. It can be bent so sharply that a ray heading almost anywhere gets curved onto a wildly different course. And in one special, crucial zone, the bending becomes so perfectly tuned that light can be caught in orbit, forced to circle the object again and again like a moon of pure light. This special zone has a name, and it is one of the most important ideas in our entire story. It is called the photon sphere, and it is sometimes described in terms of the light ring associated with it. Let me explain what it is, because everything about the shadow depends on it. At a particular distance from an extremely compact object, the gravity is precisely strong enough that a beam of light traveling sideways, tangent to the object, gets bent by exactly the right amount to curve back on itself and complete a circle. At that distance, light can orbit the object. Not fall in, not escape, but circle. This is the photon sphere, a shell where light itself is trapped in unstable circular orbits. It is a place that simply cannot exist around ordinary objects like planets or normal stars, because they are far too large and diffuse. Their actual surfaces are well outside where the photon sphere would be, so it never forms. But around something as compact as a black hole or a sufficiently compact Gravastar, the photon sphere lies out in the empty space around the object, and it becomes the defining stage on which the shadow is drawn. Now, the orbits of light at the photon sphere are unstable, and this instability is essential. A photon circling there is balanced on a knife's edge. Nudge it the tiniest bit inward, and it spirals down toward the object. Nudge it the tiniest bit outward, and it spirals away, eventually escaping to freedom. It is like a ball, balanced perfectly on the very top of a hill. The slightest disturbance sends it rolling down one side or the other. Because of this, the photon sphere acts as a kind of dividing line, a watershed for the fate of light rays that come near the object. Rays that approach and pass just outside the photon sphere get bent, sometimes dramatically, but ultimately swim back out and escape, carrying their light away to distant observers, to telescopes, to our eyes. Rays that stray just inside the photon sphere are doomed. They spiral inward and are captured, never to return to the outside universe. The photon sphere separates the light that gets away from the light that is lost. And now we can finally build the shadow. Imagine the compact object surrounded by glowing material, hot gas swirling around it, radiating light in all directions, or simply a bright background of light from behind and around it. Now imagine you are far away, looking at this scene, collecting the light rays that manage to reach you. Some of those rays come from material or background that lies well outside the object, bent only mildly on their way to you. They fill in the bright regions of your image. But when you look toward the very center, toward the object itself, you find something different. The light rays that would have had to come from that central direction are precisely the rays that pass too close, inside or near the critical boundary set by the photon sphere, and were captured or swung away. From the central region, hardly any light reaches you, because any light that tried to travel outward from there was trapped by the object's gravity or bent onto the wrong path. The result is a dark patch in the middle of your image, a region from which light is missing, surrounded by a bright ring where the surviving, sharply bent rays pile up. That dark patch is the shadow. That bright ring is the accumulated glow of light that skimmed the photon sphere and barely escaped, often circling partway around the object before flying off to you. Notice what this means. The shadow is not the horizon. The shadow is a region of missing light, and its size is set by the photon sphere and the bending of light, not by the location of the horizon itself. The shadow is substantially larger than the horizon would be, precisely because light gets captured from a zone reaching out to that critical photon sphere boundary well outside the horizon. What we call the shadow is really the imprint of how the object's gravity sculpts the paths of light, an absence carved out of the surrounding brightness by extreme lensing. It is a portrait of the object's gravitational field's effect on light, not a snapshot of any physical surface. And the bright ring around it is not the edge of a hole. It is a halo of light, woven from rays that came within a hair's breadth of being captured, and instead were flung back out toward us. I want to be very careful about what that dark patch actually is, because it is easy to picture it wrongly, and the wrong picture will mislead you at every turn. The shadow is not an empty hole punched into space, some cavity or void sitting there in the middle of the scene. And it is not a solid black surface, a dark wall or a painted disc hanging in front of the object. It is neither of those things, because it is not a thing at all. It is a direction, or rather a whole bundle of directions, along which very little light happens to reach you. When you look toward the center of the image, you are looking along paths that, traced backward, dive too close to the object, and get captured or swung away before they can bring you any light. The darkness is simply the report that those particular sight lines come up nearly empty. Aim your gaze a little to the side, along paths that skirt the object more gently, and light floods back in. So the shadow is a feature of the geography of light rays, of which directions deliver light and which do not a black object occupying a patch of space. If you could somehow fly out there and reach into the dark region with your hand, you would not touch a wall or feel the edge of a hole. There would be the object, of course, extraordinarily compact and far smaller than the shadow it casts. But the darkness itself is not something you could touch. It is an absence defined entirely by the bent paths of light. A shape drawn by what the gravity does to the rays, and nothing more solid than that. But that bright ring hides a secret structure, and it is worth peering into, because it reveals just how strange the region near the photon sphere really is. I described light that skims the photon sphere and barely escapes, curving partway around the object before flying off to you. But some rays do more than curve partway. Some make a full loop around the object before escaping. Some make 2 loops. Some make 3. Think about what that means. A ray of light approaches, gets caught in that knife edge zone at the photon sphere. circles the object once, and then spirals away toward your telescope. Another ray, aimed a tiny bit more precisely, circles twice before escaping. And the closer a ray's approach is tuned to the exact critical distance, the more times it can loop before it finally breaks free. The result is not a single clean ring, but a nested series of rings, stacked one inside the other, each one produced by light that orbited the object a different number of times. Each successive ring sits a little closer to the edge of the shadow, and each one is dramatically fainter than the last, because with every extra loop, a little more light leaks inward and is lost. These stacked features are sometimes called the photon ring, a sequence of ever thinner, ever dimmer arcs converging on the boundary of the shadow, an infinite series in principle, piling up right at the critical curve. It is one of the most beautiful predictions in all of this physics. Near an object this compact, light can circle it any number of times and still get out, layering the same scene over and over into a stack of nested images. And because this photon ring is generated entirely by the exterior gravitational field, by the bending of light near the photon sphere, it is another feature that a sufficiently compact gravastar, sharing that exterior field, could reproduce. The nested rings are a fingerprint of extreme lensing, not of a horizon. Once you understand the shadow this way, as a feature produced by the exterior gravitational field and its photon sphere, a startling realization should be forming in your mind. We established earlier that the exterior gravitational field of a compact, spherical, non-rotating gravastar can closely resemble that of a black hole of the same mass, and the photon sphere, the light ring, the whole apparatus that produces the shadow, all of it lives in that exterior field. The shadow is a creature of the outside geometry, and the outside geometry is exactly the thing a gravastar can copy. So here is the unsettling conclusion. An ultra-compact gravastar, one squeezed down so that its surface lies close to where a black hole's horizon would be, could possess a photon sphere in its surrounding space, just as a black hole does. It could bend light in nearly the same way. It could capture and sculpt the light around it, carving out a dark central region surrounded by a bright ring. In other words, an object with no event horizon at all, a gravastar with a physical surface and an exotic interior, could produce an image that resembles a black hole's shadow. The dark patch in the middle would not be evidence of a horizon, because it never was evidence of a horizon in the first place. It is evidence of extreme light bending by a compact mass, and a compact gravastar has exactly the extreme light-bending compact mass required. This is what people really mean when they speak of a gravastar hiding behind a black hole shadow. I want to be very precise about this phrase because it sounds mysterious and could easily be misread. It does not mean a gravastar is literally sitting behind some other object, out of sight. There is no second object involved. To hide behind a black hole shadow means to imitate its expected appearance, to produce the same telltale silhouette we take as the signature of a black hole, and thereby escape detection by blending in. The gravastar hides not behind a physical thing, but behind our expectations, behind the appearance itself. It dons the shadow like a costume. When we see that dark region and that bright ring and reflexively conclude black hole, a gravastar could be standing there wearing precisely that costume, and we would not know. Let me hammer the central point home because it overturns a piece of conventional thinking that many people hold without realizing it. Merely observing a dark, shadow-like region is not, on its own, sufficient to prove that an event horizon exists. The shadow proves that there is an extremely compact, massive object bending light in a dramatic way. It proves the presence of a photon sphere and the capture of light. It is entirely consistent with a black hole, and a black hole remains the simplest and most natural explanation. But consistency is not proof. The shadow is also consistent, at least in broad strokes, with a sufficiently compact horizonless object like a Gravastar, because such an object shares the exterior features that generate the shadow. To leap from "I see a shadow" to "therefore there is a horizon" is to assume the very thing we set out to test. The shadow narrows the possibilities dramatically. It tells us we are dealing with something extraordinarily compact and dark, but it does not by itself slam the door on every horizonless alternative. Now, having said all that, I owe you a serious dose of nuance, because it would be dishonest to suggest that a Gravastar's image would necessarily be a perfect, indistinguishable copy of a black hole's. It might not be, and the ways in which it could differ are exactly where our hope of telling them apart begins to live. So let me be careful here and not overclaim. I am not saying every Gravastar model produces an image identical to a black hole. I am saying that a shadow-like appearance does not by itself prove a horizon, and that some Gravastar configurations could mimic the black hole image closely. Whether the mimicry is perfect or flawed depends enormously on the specific model, and that is where the story gets rich. The crucial difference, the thing that could betray the Gravastar, is the surface. Remember, a black hole has a horizon, a one-way membrane. Light that crosses inward is gone forever, contributing nothing back to the image. The darkness at the center of a black hole's shadow is, in part, a genuine darkness of capture, of light that fell in and never came back. But a Gravastar has no horizon. It has a physical surface, and a surface, unlike a horizon, is something light can potentially interact with, rather than simply vanish into. And that opens up a whole spectrum of possibilities, depending on what that surface actually does to the light and matter that reach it. Consider the range of possibilities. At one extreme, imagine a Gravastar whose surface is almost perfectly absorbing. Light and matter that strike it are swallowed up, soaked in, with essentially nothing coming back out. Such a surface would behave, as far as the light is concerned, very much like a horizon. Light that reaches it is effectively lost from the image, just as light that crosses a horizon is lost. A Gravastar with a nearly perfectly absorbing surface would therefore be extremely difficult to distinguish from a true black hole by its image alone, because the central darkness would be reproduced almost faithfully. The absence of returning light would look, to us, just like that of a horizon. This is a key insight, and it cuts against our hopes. A perfectly absorbing surface could be harder to tell apart from a horizon than a reflective or radiating one, precisely because it mimics the horizon's most obvious effect, the swallowing of light. But now swing to the other extreme. Imagine a Gravastar whose surface is not absorbing but reflective, or radiating. A reflective surface would bounce some of the incoming light back outward. A radiating surface, one heated by the matter piling onto it, would glow with its own light. In either case, light would be coming back from a region where, around a true black hole, there should be only darkness, and that returning light could show up in the image. It might partially fill in the shadow, making the central region less than perfectly dark. It might add extra features, additional faint rings, echoes of light that struck the surface and bounced, or a subtle glow from the surface itself shining through. A Gravastar like this would not be a perfect imposter. It would carry a tell, a fingerprint of its surface, a whisper of light where a black hole would offer only silence. The exact visual appearance, whether the shadow is filled or empty, whether there are extra rings, whether there is a surface glow, depends heavily on the specific Gravastar model, on how compact it is, on the properties of its surface, and on the distribution of the glowing matter around it. Let me make that distribution of glowing matter concrete, because it shapes what we actually see far more than most people realize, and it is the very thing that lets a difference at the surface show up in an image at all. The light around one of these objects does not come from some neat, evenly glowing sphere. It comes, in most cases, from that swirling disk of hot gas orbiting the object. And a disk seen from the side does something remarkable when its light is bent by extreme gravity. The gravity lifts the image of the far side of the disk up and over the object, and folds the image of the near underside up beneath it, so that a flat ring of gas gets wrapped visually around the dark center, top and bottom, into a lopsided halo. And it is lopsided for a specific, telltale reason. The gas in the disk is orbiting at a large fraction of the speed of light, which means part of it is rushing toward you while the opposite part is racing away. Light from the side sweeping toward you is beamed and brightened. Light from the side sweeping away is dimmed. So one side of the ring blazes far brighter than the other, an asymmetry stamped into the image by the sheer speed of the orbiting gas. All of this, the wrapping, the lopsidedness, the beaming, is set by the exterior field and the motion of the gas, and here again, a compact Gravastar could reproduce it. But now bring the surface back into the picture. In a black hole, the disk's inner edge fades toward the horizon, and its light simply stops, swallowed. In a Gravastar, the gas can continue down to the surface and pile onto it. So the innermost, hottest, most sharply lensed light might not fade into darkness at all, but instead brighten toward the very center, glowing from the point of impact. The shape of that innermost light, whether it fades to black or flares to a central glow, is exactly the kind of subtle difference that the surface could carve into an otherwise near identical image. I want to dwell on that dependence, because it is important not to paint Gravastars with a single brush. There is no one Gravastar image, just as there is no one Gravastar model. A very compact Gravastar with an absorbing surface might produce a shadow nearly identical to a black hole's. A slightly less compact one, or one with a reflective or radiating surface, might produce a distinguishable image with extra structure. The appearance is a product of many choices. The object's compactness, the physics of its surface, and the pattern of emitting material swirling around it. So when we ask whether a Gravastar's image could fool us, the honest answer is, some could, some might not. And which is which depends on the details we do not yet know. That uncertainty is not a weakness of the discussion. It is precisely the map of where the answers might eventually be found. This brings us to one of the most promising cracks in the disguise, and it flows directly from the surface. Think carefully about what happens to gas as it falls toward each kind of object. Around both a black hole and a Gravastar, matter does not usually fall straight in. It spirals, forming a swirling flattened disk of gas orbiting the object, growing hotter and brighter as it spirals inward. An accretion disk. Now, follow that gas to its final destination. Around a black hole, the gas spirals down, crosses the event horizon, and disappears. It is gone. Whatever energy it carried at that final moment vanishes with it across the one-way membrane. The horizon does not shine, does not release that energy back, does not glow with the impact, because there is no impact. only a crossing into the unreachable. But around a Gravastar, there is no horizon to cross. There is a surface. And gas that spirals all the way down does not vanish. It strikes that surface. And when matter strikes a surface, energy can be released. The gas piles up, it collides, it heats, and that heat can radiate away as light. In principle, a Gravastar with a material surface could glow at its very center with the accumulated energy of infalling matter striking it. A glow that a black hole simply cannot produce because its infalling matter disappears rather than landing. This is a genuine physical difference, and it suggests a real observational test. If we watch a compact dark object accreting matter and we see at its very heart a persistent glow or radiation consistent with matter striking a surface, that would point away from a horizon. And if we see only the profound darkness of matter vanishing without a trace, with no sign of a surface being struck, that is consistent with a horizon, though, as we noted, a sufficiently absorbing surface could mimic even that. Accretion, the way matter meets its end around these objects, is thus one of our most promising avenues for telling them apart, because it forces the difference between a surface and a horizon out into the open, into light we might actually detect. Let me gather the threads of what we have uncovered, because this stretch of our journey has quietly demolished a very common assumption and replaced it with something far more careful and far more interesting. We started with that famous image, the fiery ring around the dark center, and the widespread belief that it is a direct photograph of an event horizon, and we found that it is not. The dark region is a shadow, an absence of light carved out of the surrounding globe by the extreme bending and capture of light near a compact mass. Its size and shape are set by the photon sphere, that zone where light can orbit, and by the sculpting of light rays in the exterior gravitational field, not by the horizon itself. The bright ring is a halo of light that skimmed the photon sphere and barely escaped. The whole spectacle is a product of the exterior geometry, and because it is a product of the exterior geometry, and because a compact Gravastar can copy that exterior geometry, a Gravastar could possess a photon sphere and bend light in nearly the same way, producing an image resembling a black hole's shadow. That is what it means for a Gravastar to hide behind a black hole shadow. To imitate the expected appearance, not to sit physically behind anything. And so simply seeing a shadow does not prove a horizon exists, because the shadow was never proof of a horizon to begin with. It is proof of an extremely compact, light-bending mass, which a horizonless object can also be. But the imitation need not be perfect. The surface, which a black hole lacks entirely, could betray the Gravastar. Through extra rings, reflected light, or a surface glow, depending on whether the surface absorbs, reflects, or radiates, and depending on the object's compactness and the matter swirling around it. A perfectly absorbing surface could hide the difference almost completely, mimicking the horizon's silence, while a reflective or radiating one could give the game away. And the way infalling gas meets its end, vanishing through a horizon versus striking a surface and releasing energy, offers one of our most concrete hopes for a test. So the shadow, which felt like the ultimate proof, turns out to be a mask that a Gravastar might also wear. But masks can slip, and the surface is the loose thread. To pull on that thread, and on others, we need to go beyond images of steady, glowing objects. We need to catch these objects in moments of violence and disturbance, when they are struck, shaken, or slammed together, when the difference between a wall and a one-way door might finally ring out for all to hear. And we need, at last, to confront the hardest question of all. Not just whether a Gravastar could hide, but whether nature could ever build one in the first place. We have chased the disguise as far as steady images can take us, and we have found the loose thread. The surface. A black hole has none. A Gravastar does. And wherever that surface can be made to reveal itself, in a glow at the center, in an extra ring of light, in energy released by matter striking something solid rather than vanishing into nothing, we have a chance to catch the imposter. So let us pull on that thread in earnest, and gather every tool we might use to tell these two objects apart. Then we must turn and face the hardest question of all, the one that has haunted this idea since it was born. Even if a Gravastar could hide so perfectly, could nature ever actually build one? Start with the most direct probe, the one we touched on already. Accretion. We have seen the essence of it, that infalling gas vanishes through a horizon, but must land on a surface, and that only a surface can hand its energy back. The power of this as a test lies in bookkeeping. When gas spirals inward, it carries a vast store of energy, the energy of its motion and its headlong fall. Around a Gravastar, that gas strikes the surface, and its stored energy has nowhere to hide. It turns to heat and escapes as radiation, showing up in the object's total light. Around a black hole, that same energy can be carried across the horizon and hidden from us entirely, adding nothing to the light we receive. So one strategy is to tally the energy budget, measure how much matter is falling in, calculate how much light that infall should ultimately produce, and compare it with how much light the object actually emits. If a great deal of energy seems to be going missing, swallowed without a trace, that points to a horizon. If it all re-emerges as radiation, that points to a surface soaking up the fall and shining with it. Astronomers have actually tried to use this logic on real objects, searching for the telltale glow of a surface around compact dark objects, and, in various cases, not finding the expected surface signal, which is consistent with those objects being true black holes with horizons rather than surfaces. But I have to be careful and fair here, because this is exactly where overclaiming would be a sin. The absence of an obvious surface glow is suggestive. It fits the black hole picture, but it is not an airtight proof of a horizon. And the reason is the very thing we discovered earlier. A sufficiently absorbing surface could mimic a horizon closely. If the Gravastar's surface soaks up nearly everything that hits it and releases very little back, then it produces little glow, and it looks, from the outside, almost exactly like a horizon that swallows matter without a trace. So accretion observations can constrain Gravastars. They can rule out the more talkative, radiating, reflective versions, but a quiet, strongly absorbing Gravastar remains stubbornly hard to distinguish from a black hole by its glow alone. The test is powerful against some models and weak against others. So we need more tools, and one of the most exciting comes from an entirely different kind of astronomy, one that does not rely on light at all. It relies on ripples in space-time itself. When two extremely compact, massive objects spiral together and merge, they shake the fabric of space-time so violently that waves of distortion radiate outward across the universe. Gravitational waves, stretching and squeezing space as they pass. We have detectors sensitive enough to catch these waves when they wash over the Earth, and in them we hear the story of the collision. And crucially, the final chapter of that story could sound different depending on whether the objects that merged had horizons or surfaces. Here is why. When two of these objects merge, they form a single, larger, distorted object that then settles down, vibrating and relaxing into its final quiet state. That settling down phase has a name, the ringdown. It is like the fading tone of a struck bell, a characteristic pattern of vibrations that dies away, and it carries information about the object that is ringing. For a black hole, the ringdown is shaped by the horizon. The vibrations of the newly formed black hole are damped and dissipated in a specific way tied to that one-way membrane, and the ringdown fades in a particular predictable pattern. But a gravastar has no horizon. It has a surface and an exotic interior, and an object with a surface might vibrate and settle differently than an object with a horizon, potentially producing a ringdown with a subtly different character, a different pattern of tones and fading. So one hope is that by listening very carefully to the ringdown after a merger, we might detect deviations from what a pure black hole would produce. Deviations that would betray the presence of a surface where there should be a horizon. It helps to understand why a merged object rings at all, because the reason is precisely where the surface could make itself heard. When two of these objects collide and merge, the newborn object is left lopsided, distorted, wobbling, and it cannot stay that way. It has to shed its distortion and settle into a smooth, quiet final shape, and the only way to shed that energy is by radiating it away as gravitational waves. As it does, it vibrates at a specific set of natural frequencies, its own characteristic tones, each fading over its own span of time. These tones are not arbitrary, they are fixed by the properties of the object itself, chiefly its mass and its spin. The way the pitch of a struck bell is fixed by the bell's shape and material. Measure the tones and how quickly they die, and you're uncovering the identity of the thing that is ringing. And here is the crucial part. What sets those tones is not only the object, but the condition at its boundary, the rule for what happens to a wave that travels inward and reaches the object's edge. For a black hole, that rule is absolute. A wave that reaches the horizon goes in and does not come back. A purely one-way, purely absorbing boundary. That specific boundary condition is baked into the black hole's characteristic tones. But a gravastar's boundary is not a horizon. It's a surface. And a surface does not have to absorb everything. It can reflect. Change the boundary rule from purely absorbing to partly reflecting, and you can change the tones, subtly shifting their pitch or their fading, or adding new ones. So the ringdown is not just a fading note, it is a note whose exact character encodes whether the object that rang had a one-way membrane or a wall at its edge. Listening for a ringdown that does not quite match a pure black hole is, in effect, listening for the acoustic signature of a surface. And there is a more dramatic, more specific possibility that arises from the surface, one that has generated a great deal of excitement, and that I must present with real caution, because it is easy to get carried away. It is the idea of gravitational wave echoes. Think again about the difference between a horizon and a surface. When the merger sends gravitational wave energy inward toward the newly formed object, a black hole's horizon would simply absorb that energy. It crosses the one-way membrane and is gone. But a gravastar has no such membrane. It has a surface and an interior structure. And so some of that gravitational wave energy, instead of being absorbed and vanishing, might be reflected back outward by the surface or the interior. That reflected energy would then travel out, perhaps get partially bent back inward again by the surrounding gravitational field. bounce off the surface once more, and escape again, and so on. The result would be a series of repeating pulses arriving after the main gravitational wave signal. Faint, delayed repetitions, like an echo returning again and again after a shout in a canyon. These proposed delayed pulses are what physicists mean by gravitational wave echoes. Their presence would be a striking sign of a surface, of a reflecting boundary where a black hole would have only a horizon. Their absence would be consistent with a clean horizon. Now here is where I must plant my feet and be scrupulously honest, because this is precisely the kind of idea that can be badly oversold. Gravitational wave echoes are a fascinating, well-motivated proposal, and searches for them in the data have been carried out. But echoes have not been established as confirmed evidence for gravastars or for any horizonless object. There have been intriguing hints in some analyses, claims that faint echo-like features might be present in certain gravitational wave events, but these claims have been contested, debated, and are not accepted as solid detections. The signals, if they exist at all, are subtle, buried in noise, and easy to mistake for statistical flukes. So let me say it plainly. Echoes have not been confirmed. They remain a proposed signature, a thing to look for, a tantalizing possibility, not a discovery. Anyone who tells you that gravitational wave echoes have proven the existence of gravastars, it is getting ahead of the evidence. The right posture is careful hope. This is a promising avenue that might one day reveal a difference. And we are actively listening, but we have not heard it clearly yet. Beyond accretion glow and ringdown and echoes, there are still other ways the surface and interior might show themselves, and they cluster around moments of interaction and disturbance. One involves how these objects respond to being stretched. When two compact objects orbit close together before merging, each feels the tidal pull of the other, its partner's gravity stretching it slightly. How much an object yields to that pull is captured by a property called its tidal deformability, and it is one of the cleanest windows we have onto whether an object has any internal structure at all. But why should a black hole of all things refuse to bulge when another object's gravity pulls on it? It seems almost paradoxical. Everything else in the universe deforms when tidally stretched. The Earth's oceans rise into tidal bulges under the moon's pull. Stars are drawn into teardrop shapes by close companions. Neutron stars stretch measurably before they merge. Yet a black hole, in the idealized case, develops no such bulge at all. Its tidal deformability comes out to essentially zero. The reason cuts to the heart of what a black hole is. To develop a tidal bulge, an object needs internal structure, material that can be pulled and piled up on the near and far sides, a body with parts that can be rearranged. A black hole, in the classical picture, has no such material to rearrange. It has a horizon and, within it, no ordinary structure that could gather into a bulge in the usual sense. It responds to the external pull, but it does not deform in the way a body made of stuff would. A gravastar is different precisely because it does have structure, a shell, an interior, real physical layers that another object's gravity could stretch and distort. And so a gravastar could carry a non-zero tidal deformability, where a black hole predicts zero. The objects most likely to be gravastar imposters are also among the heaviest, and the heaviest objects deform least of all. So the imprint we would be hunting for is faintest exactly where we most want to see it, which is a large part of why a clear detection has stayed out of reach now. How could we ever measure such a thing across the vastness of space? The answer is one of the more elegant tricks in gravitational wave astronomy. When two compact objects spiral toward a merger, they orbit faster and faster, and the gravitational waves they emit sweep upward in frequency, a rising chirp. If the objects are perfectly rigid and undeformable, that chirp follows one exact pattern. But if either object deforms under its partner's tidal pull, the bulge it develops subtly changes how the two objects attract each other, which subtly changes how quickly they spiral together in those final orbits, which in turn subtly shifts the timing, the phasing of the gravitational waves we receive. A deformal object leaves a faint imprint on the wave, hurrying the final moments by a tiny amount compared to a rigid one. By measuring the phasing of the chirp with enough precision, we can, in principle, read off how deformable each object was. Detect a clear tidal imprint from an object we expected to be a black hole, a non-zero deformability where zero was predicted, and we would have a strong hint that the object has internal structure. It is not a black hole at all, but something with a surface and an interior. The measurement is exquisitely delicate, near or beyond the reach of current detectors for the objects we most care about, but it is a real and direct handle on the one thing a black hole is not supposed to have: a body that can be stretched. Then there are surface interactions in a more general sense, the whole family of effects that arise simply because there is something there for things to hit, reflect off, or interact with, where a black hole offers only a horizon that swallows. And underlying all of these is the recurring theme we keep returning to: the difference between a wall and a one-way door. Every test we have discussed, accretion, ringdown, echoes, tidal deformability, is at bottom an attempt to sense whether the object's edge can still interact with the outside universe, or takes in everything and gives nothing back. That is the single physical distinction driving all of it, and it is why the surface, that loose thread, is the key to everything. But I have been quietly setting aside a major complication this whole time, and I need to bring it forward now because it makes every one of these tests harder, and the whole subject messier and more realistic. Real objects spin, and spin changes everything. The clean, perfect impersonation we described, the exact match of exterior fields, the tidy photon sphere, the neat ring down, all of that was for idealized, non-rotating spherical objects. But the dark, compact objects we actually find in the universe are very often spinning, sometimes at tremendous rates. And a rapidly rotating Gravastar is theoretically far more complicated than the idealized spherical model. Rotation breaks the perfect spherical symmetry that made the exterior match so clean. It distorts the object, flattening it, twisting the space-time around it in ways that no longer correspond to the simplest solutions. The interior physics, the exotic vacuum, the shell, all become much harder to model when the whole structure is spinning. Whether a rapidly rotating Gravastar is even stable, whether it can hold together against the stresses of rotation, whether its exterior still mimics a spinning black hole as faithfully as the non-rotating versions mimic a non-rotating black hole, these are genuinely difficult questions that push at the frontiers of the modeling. So the idealized story we told is cleanest exactly where reality is least likely to be clean. Rotation is both a complication that muddies our simple picture and potentially an opportunity, because the differences between a spinning Gravastar and a spinning black hole might be larger and easier to detect than in the idealized non-rotating case, if only we can work out the theory well enough to know what to look for. Now we arrive at the deepest and most stubborn problem of the entire concept. The question that no amount of clever observation can settle on its own, and the one that keeps Gravastars firmly in the realm of hypothesis. How would a Gravastar actually form? We have spent all this time describing what a Gravastar would be like if it existed, how it would look, how it might hide, how we might catch it, but we have quietly assumed the thing into being. And that assumption is where the concept faces its hardest challenge. Formation is, without exaggeration, one of the largest unresolved problems the Gravastar idea faces. Let me explain why this is so serious. When a massive star runs out of fuel and its core collapses, we understand, at least in broad terms, how that collapse can produce a neutron star, or if there is enough mass, how it can proceed to form a black hole. The physics of gravitational collapse, as we understand it, seems to lead naturally toward horizons and singularities when enough mass is compressed into a small enough space. What is not at all clear is how that same collapse could instead halt at just the right moment, in just the right way, to produce a Gravastar. Remember what a Gravastar requires: an interior somehow transformed into an exotic vacuum state, a razor-thin shell balanced with exquisite precision at just the right radius. The whole collapse arrested a hair's breadth before a horizon would form. For nature to build this, ordinary collapsing matter would have to undergo some transition into that exotic vacuum state, and the timing and the balance would have to come out just so. And we do not have a compelling, worked out account of how realistic, messy, infalling stellar matter would actually do that. We can describe the finished object. We cannot yet describe a believable path by which nature arrives at it. To feel the weight of this problem, follow a real collapse in your mind. A massive star spends its life fusing lighter elements into heavier ones, building up an inert core of iron at its heart, iron being the ash that fusion can no longer burn for energy. That core is held up, for a time, by a stubborn quantum resistance among its packed electrons. But as more iron rains down and the core grows heavier, that resistance is overwhelmed, and in a fraction of a second the core gives way and collapses inward at a sizable fraction of the speed of light. From here, as we understand it, the story forks. If the collapsing core is not too heavy, it slams together, rebounds, and settles into a neutron star, blowing off the rest of the star in a supernova. If it is heavy enough, nothing halts the fall, and the matter plunges on until a horizon closes over it, and a black hole is born. Now ask where, in that violent, headlong plunge, a Gravastar is supposed to appear. For a Gravastar to form, that infalling matter would have to stop being ordinary matter partway down, transforming into the exotic vacuum state with its negative pressure, and it would have to do so at exactly the right instant, precisely as the collapsing surface approached the radius where a horizon would otherwise seal shut. Not a moment too early, and not a moment too late. The transition would have to switch on across the whole core in near perfect balance, arresting a collapse that is already moving at enormous speed. What physical process triggers that transition? What causes ordinary matter, falling faster and faster, to convert into an exotic vacuum at just the critical radius rather than sailing past it into a horizon? We do not have an answer. There is no established mechanism, no natural trigger we can point to. That would make a real collapsing core choose the Gravastar ending over the black hole ending. The finished object may sit peacefully in our equations, but the road that leads to it, out of a genuine stellar death, is missing. This exposes a distinction that is absolutely central to thinking clearly about the entire subject, and I want to state it as carefully as I can. There's a profound difference between constructing an object that is mathematically possible and demonstrating that such an object can actually form in nature. Physicists can write down a mathematical description of a Gravastar, a configuration that satisfies the equations of general relativity, a self-consistent object on paper. That is a real achievement, and it is what makes the Gravastar a serious idea rather than a fantasy. But a mathematically permitted configuration is not the same as a physically realizable one. The equations of a theory can allow structures that nature never actually assembles, because there is no realistic process that leads to them. Showing that a static Gravastar can exist as a solution to the equations does not show that gravitational collapse in the real universe would ever produce one. Those are two entirely different claims, and the gap between them is where the Gravastar's greatest vulnerability lies. It is one thing to say the object is not forbidden, it is quite another to say it is formed. And on the question of formation, the honest answer today is that we do not know of a convincing mechanism, and this remains a deep and unsolved difficulty. And closely tied to formation is the question of stability, which is just as thorny and just as model dependent. Even if a Gravastar could somehow come into being, would it stay in being? Would it hold its delicate balance over time, or would some small disturbance grow and grow until the whole structure fell apart, collapsing into a black hole after all, or dispersing? Stability is not something we can simply assume. It has to be checked, model by model. And the answer depends heavily on the specific Gravastar model in question, on the properties of the shell, the equation of state of the interior, the details of the transition layer. Some models have been analysed and found to be stable under certain conditions. Others may not be. There is no blanket guarantee that Gravastars in general are stable. Stability is a property that must be established for each proposed configuration, and it cannot be presumed to hold universally. So even setting aside formation, the question of whether a given Gravastar would persist is a live and unsettled one. Let me now step back and place the Gravastar honestly among its cousins. Because it is not the only proposed alternative to a classical black hole, and I do not want to give the impression that it stands alone, or that it is simply a black hole with the inside painted differently. There is a whole small menagerie of proposed compact objects, and the Gravastar is one member of it. There are boson stars, hypothetical objects held together not by exotic vacuum, but as vast coherent clumps of a certain kind of hypothetical particle. A completely different way of building a compact, dark, star-like object without a horizon. There are wormholes, proposed tunnels, or bridges connecting different regions of space-time, which are a different kind of exotic object entirely. More about connecting distant places than about replacing the interior of a collapsed star. There is the notion of a regular black hole, which is an attempt to describe a black hole that keeps its event horizon but replaces the central singularity with some smooth, finite core. So it still has a horizon, unlike a Gravastar, but no singularity. And of course, there is the ordinary black hole itself, with both a horizon and a singularity, the standard picture that all of these alternatives are reacting against. The Gravastar is distinct from all of these. It differs from the boson star in what holds it up and what it is made of. It differs from the wormhole in that it is a compact object standing in for a collapsed star, not a tunnel between places. It differs from the regular black hole crucially in that the regular black hole keeps its horizon, while the Gravastar does away with the horizon entirely, replacing it with a surface. And it differs from the ordinary black hole in lacking both the horizon and the singularity. I raise these cousins deliberately but briefly, because it would be easy to let them swallow the whole discussion, and they are each stories of their own. The point of mentioning them is simply to locate the Gravastar precisely. It is a horizonless, surface-bearing, exotic, vacuum-filled, compact object, and that combination is what sets it apart. It sharpens the picture to line these cousins up by how each one treats the two features we have been chasing all along, the horizon and the singularity, because that is really the axis the whole family is organized around. The ordinary black hole keeps both, a horizon on the outside, a singularity at the center. The regular black hole keeps the horizon but abolishes the singularity, smoothing that troublesome central point into a finite core. So it is still very much a hole you can only fall into, just without the infinity at the bottom. The wormhole does away with the idea of a central endpoint entirely, replacing the interior with a passage that leads elsewhere rather than a floor that matter piles onto. A fundamentally different geometry aimed at connecting regions rather than terminating collapse. The boson star, like the Gravastar, has neither a horizon nor a singularity, but it reaches that state by a different route, as a diffuse, self-supporting cloud of a hypothetical field rather than a sharp shell wrapped around an exotic vacuum, and it is generally far less compact. So it does not press right up against the black hole disguised the way an ultra-compact Gravastar can. And the Gravastar sits in its own particular seat. No horizon, no singularity, but not diffuse, and not a tunnel. Instead, a razor-thin surface poised almost exactly where a horizon would form, wrapped around an interior of repulsive vacuum. Seen this way, the Gravastar is the alternative that gets closest to imitating a black hole from the outside, while sharing the least with it on the inside, which is exactly what makes it the most slippery of the imposters. And this lets me correct one more possible misunderstanding before we close, one that is worth stating outright. A Gravastar is not simply a black hole filled with matter. That is a tempting but wrong way to picture it. It is not that you take a black hole, keep its horizon, and stuff some stuff inside. The whole point is that the horizon is gone. The Gravastar is a fundamentally different object, one in which the collapse never completed, the horizon never formed, and the interior is not ordinary matter crammed into a hole, but an exotic vacuum state doing something no ordinary matter does. To think of it as a filled-in black hole is to miss the essence of the idea. It is a different ending to collapse, not a modified version of the black hole ending. So let us draw together, with as much honesty as we can muster, exactly where this leaves us, sorting carefully among the different levels of confidence, because keeping these straight is the whole discipline of thinking well about this subject. At the first level, there is mathematical possibility. Physicists have written down Gravastar configurations that satisfy the equations of general relativity, beginning with the original idealized 3-region model and extending to a whole family of later, more elaborate models with thicker shells, different interiors, and different assumptions. These are real constructions on paper. At the second level, there is theoretical modeling of how such objects might behave, how their exteriors could mimic black holes, how their surfaces might interact with light and matter, how they might ring after a merger, how they might deform under tides, how rotation would complicate everything. This is active, serious work, and it tells us what to look for. At the third level, there are proposed observational signatures. The central glow from accretion striking a surface, deviations in the ringdown, the tantalizing possibility of gravitational-wave echoes, measurements of tidal deformability. These are things we could in principle detect, and we are trying. And at the fourth level, there is actual confirmed evidence, and here the ledger is empty. No Gravastar has been observed. No echo has been confirmed. No dark object we have found has been shown to be a Gravastar rather than a black hole. The most natural reading of everything we have seen so far remains that these objects are black holes, and Gravastars remain an unconfirmed alternative worth taking seriously and worth testing, not a rival that has been established. Which brings us, finally, back to the question that started this whole journey, and which now stands before us stripped of easy answers. We photograph a dark silhouette, ringed with fire, and call it a black hole. We watch stars swing around invisible masses and call them black holes. We hear the ripples of colliding giants and call them black holes. And in every case, the thing we truly detect is an object that is extraordinarily massive, extraordinarily compact, and extraordinarily dark. What we have discovered following the Gravastar idea to its end is that all of those observations are about the outside, the mass, the compactness, the bending of light, the exterior field, and that the one feature which would truly define a black hole, the event horizon itself, that one-way membrane sealing off a piece of the universe forever, is precisely the thing we have never directly seen and perhaps cannot easily prove. A sufficiently compact, horizonless object could, in principle, imitate nearly everything we currently observe. So here is the central unresolved question, the one we are left holding as the lights come down. Are the objects we call black holes truly bounded by event horizons, genuine points of no return, singularities cloaked in one-way surfaces? Or could at least some of them be something else? Ultra-compact horizonless objects, Gravastars or their cousins, wearing the mask so well that everything we have measured so far, the orbits, the shadow, the ringing of space-time, could be produced without any horizon at all? We do not know for certain. The evidence we have is consistent with horizons, and black holes remain the simplest explanation. But consistency is not proof, and the disguise runs deep. Somewhere out there, if the hypothesis is right, an object could be sitting in plain sight with a surface instead of a horizon, and a strange vacuum instead of a singularity, casting the very shadow we take as proof of the abyss. Whether such things exist, whether nature ever builds them, and whether we will one day catch one betraying its surface, remains one of the genuinely open questions at the edge of what we understand about gravity, about collapse, and about the darkest objects in the universe.